So we really have to change our perspectives with this polymer lesson. It's not going to fit nicely into the other families in terms of drawing structures. These are going to be ginormous molecules. Okay? So polymerization, we have the word poly in front, it means many. And the molecules that some of my other grade 12s have put up in my room are really good examples of what to get your head into. This would be a teeny tiny little polymer that has 100 carbons. Even this would be pretty tiny in the polymer world. I think this is 200 or 300 carbons in a row. I know it's hard to see the actual C's, but every inch is a CH2. Okay? Polymers often have masses of millions of grams per mole. So really long chains, and they all weave around each other, and that makes all the plastics that we use, and often makes them flexible because they can just bend around each other. So we have a different set of terminology. Instead of calling the starting pieces reactants like we normally do in chemistry, we refer to them as monomers. Okay? So we have mono, one unit, is going to turn into many units. Okay? So this word replaces reactants. The product we refer to as not a product, but we refer to them as a polymer. Okay? And we're going to have to draw a short form for it. Okay? Because clearly I'm not going to make you draw this. That's impossible. We can't put it in books. I can't write that either. Okay? So we're going to see repeating patterns. So we're going to jump into the first of two types of polymerization. We're going to do addition polymers first, and then we'll do condensation, and then that will wrap up the first half. Main key to addition polymerization is the fact that we're breaking a double bond to create the possible connections. Thinking back to AP chemistry, and it's come up already, that second bond is a pi bond that's easily broken. So what we're going to see happen all the time in addition chemistry is that pi bond, that second bond break. When it breaks, it frees up a connection on each side. And we're just not going to add a little molecule or atom like Br or Cl like we did before. We're going to connect another one of these monomers to each end. And every time we connect a monomer, we connect something on one end and it frees up another end to keep growing. So we get these two bonds, which allows continuous growth. So we're going to start by looking at what happens if we put two ethines together, and then we could propagate this out 1,000,000 times. We're going to break the pi bond, or the second bond. And as we work our way up, we'll get bigger molecules, but only focus in on the double bond. Don't look at any carbon-carbon single bonds. Okay? So you could, in theory, have 5 carbons with one double bond. We're only going to alter that piece. When this bond breaks, we get an extra bonding capacity spot here and here, and this carbon is going to connect to that carbon. It's also the carbon on the end of the double bond. So make sure you connect a carbon at the end of a double bond to another carbon at the end of a double bond. So we'll end up getting 1, 2, 3, 4 carbons all connected. Across the first two is 4 H's. And the second is 4 H's. And we end up with these dashes at the end that it will keep growing, Or if you want to stop building your polymer, we're not going to do this, but to stop them from growing, they just throw in a chemical that's going to pop in and terminate here. So maybe add a bunch of chlorine or something that's going to go in and pop and stop it. Okay, but I'm leaving that blank because we're not doing that step. So that's just 2 units being connected. How we're typically going to draw this is, you know, there might be millions of these, and we're just going to say there's n of them. Often your math teachers use n to represent any whole number. Okay, so that we have n of those, could be 10, 100, a million, a billion. And we're going to have a repeating unit. We're just going to show what that unit does n times and show the pattern. These kind of dashes that I put to nowhere, those are now showing coming in and out of the bracket. So we have 2 carbons. The double bond has to break in order to get this repeating unit. And in this polymer, it's all H's. If we look at our IUPAC names, this guy we haven't altered. Okay, we already know how to name it. This is ethene. No number needed. For the polymer, the naming convention is you add poly in front of whatever the monomer was. So because the monomer to make this is ethene, this is polyethene. And you really have to watch your understanding. You might incorrectly think, oh, polyethene, that's an ene. The product must be an ene. No, this ene is coming from the double bond that used to exist in the monomer. There's no double bond, even though it's called polyethene. Now, you won't get tested on this, but the connection to everyday life is if you look at recycling code 2 or recycling code 4, these are both forms of polyethylene. One is high density and one is low density. I'm pretty sure all the milk jugs are 4. Okay? And companies need these recycling codes to know to put all the polyethylene together and recycle those together, not mix it up with other plastics. Second, just a little bit more complicated, we're going to start with propene this time. Which means when we put a bunch of them together, we're going to get polypropene. So if I ask you, what's the classification of these? You're going to say monomers now. Okay. If I ask you, what's the IUPAC name? You're not going to say monomer as the name. That's a classification. You're going to call it propene and polypropene, or the classification of what you make is a polymer. So now we have to do the same thing and not get bothered by that extra carbon that's thrown in. There's my double bond that's going to break. There's my double bond that's going to break. This carbon at the end of the double bond can connect to that carbon at the end of the double bond. We can't do anything to this, what looks like a methyl group hanging down. We're not going to get any chemistry there. That's going to keep hanging down. So we have 2 carbons. That's where my double bond used to be. This carbon has a CH3 coming off of it. This carbon now has 2 H's. And then I'll move to the second unit. There's the double bond I added across. We end up with a polymer that's a bit branched. It's not a nice straight line like polyethene. Okay? Polypropene has a more complex structure. Now, the more typical way to draw it is just to say n of these, and we're just going to show that repeating pattern n times. So I break the double bond. And whenever you break the double bond, there's always 4 connections around that double bond. So sometimes it's helpful to circle them or visualize right in on what are those 4 connections, and it's always 4 in addition chemistry. So you have H on the top, CH3, H. Okay. And these are your number 3 recycling codes. I'm hoping that most have flipped over plastic bottles and seen those numbers. I see there's a couple bottles in the room. I imagine this, probably a 5. No, this is actually a 4, so this is high density polyethylene. A lot of the water bottles are 5s. If you buy a throw out water bottle, it's a 5 most of the time. So we're not going to go through all of the plastic codes you're used to seeing. We'll do one more, and then I'll just make it a little more complex to wrap up addition, and then we'll move into condensation. So I'm not going to do the two styrenes coming together and then do the repeating pattern. I'm going to jump right into the repeating pattern. N styrene. So the monomer here is styrene. So it's got one of those benzene rings, and then it's got a double bond coming off of it that can allow the polymerization. It's going to repeat n times and identify our 4 things, H, 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 benzene ring, or you may want to call it a phenyl as a side group. Okay. So that's the 2 carbons that were part of the double bond. No double bond anymore. 3 of the connections are H's, and we have a phenyl. I'm going to use the line structure to draw quickly. As is in the heading of this section, the polymer is polystyrene. Very well used plastic. These are your number 6s, but they're often really hard to recycle. Okay, this is your styrofoam. Okay. Now you'll see it come in 2 different forms. They'll pump air in with it when they make it to make styrofoam that's really light and fluffy, or if they don't pump air into it, it's really hard and dense. I think that Tim Hortons brown cups are number 6s. I think they're a form of polystyrene, but they don't have the air pumped into it, so it doesn't look like styrofoam, but it's the same plastic at its heart. So those are common ones. Okay. Now you can mix different monomers together, and chemists are always trying to figure out, companies like DuPont is heavily into the plastic making and making polymers, and they're always trying to figure out, how can I mix different monomers together and make a product that has mass market appeal? And a lot of times they come up with something by accident. They try something and they hope it has nice properties, and it doesn't, but it works for something else. That's how Scotch tape was developed. Okay? They were trying to make a glue, and the glue didn't work right. It would stick, but then it would come off. It wouldn't stay. And they're like, oh, but that can be handy to have tape or glue that sticks and comes off. So you can stick it together in a roll, okay? But then it's quite handy that it unsticks. You know, there's the glue unsticking. So what was actually an accident ended up being a very useful product, a glue that doesn't stay stuck. Okay. So let's see what happens if we mix 2 different monomers. So I have, what, bromoethene here and tetrachloroethene there. Okay. Now, if we mix those together, we're going to keep getting one of those and one of those and one of those and one of those, particularly if you mix them in the right ratio. We're not really going to go, it obviously takes a bit of planning and engineering to get it to alternate. We're going to get a repeating unit with one of each in it. The first piece is going to be BRHHH, and the second will be all Cl. So now we have 2 carbons from the first unit followed by 2 carbons in the second unit. Got our Br, our H. And that's going to repeat n times. Last, to end this, we're just going to work backwards. Okay. You might be given, it's started seeing a lot of these on the diploma the last 4 or 5 years from Alberta Ed. Instead of going forward, they test students, can they go backwards based on what they've been taught? What if you had this polymer, and they'll ask you what monomer made this, A, B, C, or D on the diploma, to test if you have a good understanding of the bonds. And they might ask you what family, or actually draw it. Okay? So we're going to need 2 carbons in our monomer. We've got to identify the 4 things connected to it. So we got a Cl, a Br, an H, and an H. And, you know, one common incorrect answer would be to draw this as one of the, maybe your A incorrect answers. They put an ane in as the monomer. Okay? You have to realize this is an ane, but it doesn't come from an ane. You have to put in that double bond. The monomer has to be an ene. And you're going to need N of those. And they'll come up with 3 incorrect monomers and 1 correct monomer to make this. Okay? I've even seen, and you could get something like this and be asked what 2 monomers made it. It's a little bit more tricky, but still doable. Okay. They could give a long repeating pattern of just 1 monomer, and you have to figure out, is that 2 different monomers that made it, or just 1, and answer the question. Okay. So that ends addition, polymerization. Take a double bond, break it, and put things together. I'm going to do one example. It's going to be a lot more drawing of a condensation polymer next. Yeah, it does. This is really complicated, okay? I kind of liked polymers in university and took a whole bunch of 4th-year university courses. Alberta Ed is saying it's in the curriculum that you have to go over this light intro to polymers, but it's really complicated. And we're not getting into the catalyst you need to get it started, what you need to stop it, the reaction conditions. So your question is good. We did catalyst all the way along. This is like a really crazy light intro to polymers because of how complicated it is. So don't worry about any of the catalysts you need. And it gets complicated. There's at least 3 different ways to do this, which have totally different. You can use positively charged cations, negatively charged anions, or most often radical chemistry, something with a single electron. An orbital with just 1 electron is a radical. So the answer, it would be a whole university course to answer your question, which is why it's being omitted. Any other addition questions? So last slide of the morning, condensation polymers, which undergo it's a dehydration reaction. It's the identical chemistry to our esters, but it's named, it's categorized differently because it happens over and over and over again. What makes it different than our ester chemistry is all of the monomers have two functional groups. The alcohol has two hydroxyl groups and the carboxylic acid has two carboxyl groups. So it can connect in both sides. So similar to our other polymerization, we're going to take a whole bunch of those, a whole bunch of the difunctional acid and a whole bunch of the difunctional alcohol. So we need to notice that there is a carboxyl group, C double bond OH on that side. So an alcohol can react on this side of the acid and grow the chain that way. But we have another carboxyl group, C double bond OH on that side. So it can also grow to the right. And the alcohol can do the same thing. We have a hydroxyl group, so that can grow to the left, and it's got one on the right. And that's what makes this a polymer and not just an ester like we did on Monday. Now in your notes, you might be able to write this here. It's going to be a fair bit of drawing for me, and I want to make it fairly big. So I'm just going to stick the polymer underneath. Okay? So I can write big, but it really fits up here. Now, when we do an esterification reaction, we end up with the alcohol connecting to this C, and that OH pops off and starts the connection. So this dash comes from this removal and a connection going in there. So that's where I'm going to start this repeating pattern. So this C is that carbon, double bonded to an O. And we could have, an alcohol connecting there. Then we've got an aromatic ring. Because it's easier for me to draw, I'm going to use the line structure. I think it keeps it clearer and better for students to learn. So I just replaced the formatting of a structural diagram to a line structure. Now we're at this carbon. I go to this C double bond O. And again, it's the OH that comes off. Now we're going to connect this O connects to that C. So that's gone. I've got the alcohol now, and I'm just going to switch colors to emphasize when we popped in the alcohol piece. There's two carbons. And then I've got to get my repeating pattern right. I didn't show any O's at the beginning, so I've got to show an O at the end to get the count right. Okay? And then that's going to repeat. So this O would connect to another black acid in another unit. So you have to in your mind, try to visualize this happening over and over again and growing like something I have on the top of the board. We have a question? Did I, yeah, I added an extra C, I think. I believe. Yeah, I threw in an extra carbon I shouldn't have. So now there's no name. The polymonomer is only for addition chemistry, so you can't name this. Okay? In general, we're going to call this a polyester, but that's not the name just for this. Anything that's condensation, polymerization, that is bifunctional, you're going to make a polyester. Okay? There's probably many in here wearing polyester clothes that's made just like this. Okay? Now, one particular polyester was invented by DuPont, and they trademarked it and called it nylon. Okay? Only DuPont can call that particular ester nylon. Anybody can make polyester. Okay? So somebody can, steal or use what DuPont's created, but not use their name. Okay? We're often used to trademark legal names: Kevlar, DuPont. Okay? Those aren't chemical names; they're trademark names that companies have made a product, put a name to it, and only they can use it. Another question? Yep. Yes, I haven't included my water here. And it's actually going to be 2 waters. You're going to get a water from each end. Now, you're typically not asked to balance these. They get messy. There's things coming off. We're doing repeating patterns, but we do get water coming off the same as we do in an ester. So I color-coded this, the acid piece black and the alcohol piece blue. You probably don't even want to write this down, but if I was trying to do almost like a picture or a model of this, would see, and I'm just going to use line segments, it's going to be like acid, alcohol piece, acid piece, alcohol piece, acid piece, alcohol piece, and that's just going to repeat millions of times over and over again. But I've just shown 2 of them up above. Okay? So all kinds of polyester. I believe the nylon, the trademark one, nylon, is called nylon 6,6. I think there's 6 carbons in the alcohol and 6 carbons in the acid, if I'm remembering correctly. Okay. These are quite flammable materials. You have to be really careful of polyester. I once saw a ski coach with his polyester jacket, and he put it near a propane heater in a tent, and it was just gone instantly, almost like it just evaporated. It just went, like in 3 seconds, his jacket was gone. I've never seen something combust so quickly. So be careful with your polyesters. Okay, so that completes the main polymers. Okay, particularly historically, addition was the most important to know. We're still a little biased at ND. Our tests are a little addition heavy, but we've had to expand this again due to the diploma questions coming from more polymers. So esterification is more likely, and then after the break, we need to go through a few more types, those biological ones. So amino acids making DNA is polymers. You eat lots of pasta and starches, those are polymers. Okay, polymers made out of sugar. Okay? So we'll go through a bunch of those biological polymers, and then we've done the whole course.